Okay, welcome back, everyone. Hope you had a great lunch. I'm David Kowick. I'm the Chief Scientist of Ocean Visions, and today, for this next hour, we're going to be talking about something really exciting. We're going to be talking about in-water testing of ocean-based carbon dioxide removal technologies. Now, for the last day or two, you've heard about the importance of research, development, and testing so that we can have real-world information about efficacy and impacts. When Ocean Visions got started on this work a few years ago, a lot of the people that we talked with and a lot of the companies that we interacted with were still in an ideation stage. And now fast forward several years, fast forward 3 years, fast forward through a pandemic, and a lot of these companies are putting technologies in the water that are giving us critical information about efficacy and impacts that can all help us make more well-informed decisions about the scope and scale of all the relevant technologies that we know are going to be needed to meet the carbon dioxide removal requirements that we've now locked ourselves into. And so I'm really excited for this panel today. I'm going to introduce our speakers. We're going to hear a little bit from each of the speakers about the early results from their in-water testing, and then we're going to have a bit of a panel discussion. So without further ado, let me introduce the speakers. Sitting all the way on the right here, we have Dr. Nathan Walworth, who is an adjunct assistant professor at the University of Southern California and VP of Science Strategy and Communications at Vesta. Dr. Walworth has a background in biological oceanography and social entrepreneurship. That's a combination of words you don't hear very often. He's also the co-founder of the Nexus Futurism Group and Business Accelerator. And at Vesta, he helps lead the scientific programs along with the ethical application of their ocean CDR technology. Sitting next to him is Dr. Matt Eisenman. Matt is the CTO, Chief Technology Officer, and co-founder of EbCarbon, and he's also an associate professor at Stony Brook University. Matt has spent the last decade developing technologies that capture CO2 from the air using natural ocean atmosphere equilibrium. He received his bachelor's in physics from Princeton and a PhD from Harvard. And before this, he was a member of the research staff at Xerox PARC and a physicist at Brookhaven National Lab. He's also served as technical advisor at Google X, where he led Project Foghorn. And finally, joining us virtually, can we pull Anna up, please? Joining us virtually is Anna Grohn. Anna is a master's student in biological oceanography at the Guiomar Helmholtz Center for Ocean Research in Kiel, Germany. Her research interests lie in the field of marine biogeochemistry with a particular focus on environmental stoichiometry and the feedbacks associated with the plankton community in a changing ocean. She's dedicated to evaluating the potential of our oceans to mitigate climate change and advancing our understanding of the impacts that ocean-based negative emission technologies may have on marine ecosystems. So we have a really esteemed set of panelists, and I am going to turn it over to Anna first, who's going to share some early results from their mesocosms in Norway, and then after that we'll hear from Nathan, and then after that Matt. Take it away, Anna.
Yes, thank you very much, David. Like David already said, my name is Anna Grohn, and I'm researching on the environmental impact of ocean alkalinity enhancement, with the particular focus of how the biogeochemistry in the suspended material responds. So first, I'd like to provide you with some background information. So what actually is ocean alkalinity enhancement, or short OAE? OAE is one of the ocean-based carbon dioxide removal techniques with the aim to enhance the chemical uptake and storage of atmospheric CO2 by increasing the surface water alkalinity. And this can be achieved, for example, through the dissolution of certain minerals. However, it is yet largely unknown how this technique might impact the marine ecosystem. So our research aims to investigate the potential biological consequences of OAE and also related to the application of different mineral types. So if the chemical properties of the seawater change under OAE, it can potentially cause changes, especially at the bottom of the food web, which can then trigger shifts in other parts of the community and can cascade throughout the whole ecosystem. And generally, the elevated alkalinity is considered to benefit especially calcifying organisms. But on the other hand, certain minerals, the silicate-based minerals, additionally introduce silicate into the system and therefore might benefit silicifying primary producers. So the approach of our research is to assess large-scale environmental consequences of ocean alkalinity enhancement under natural conditions. So in our recent experiment, we deployed 10 offshore mesocosms in the Raunefjord, which is close to Bergen in Norway. And these are large floating frames with 20-meter long and 2-meter wide mesocosm bags mounted on them. And in each bag, an ambient water parcel is enclosed, in which we can then change the water chemistry according to our research and observe the response of the whole plankton community over time. So we deployed this 10 mesocosms, and then we established an alkalinity gradient over 5 levels and simulated the application of 2 different mineral types, a calcium-based mineral type and a silicate-based mineral type. And to then track the response of the ecosystem to this treatment, we collected samples of each mesocosm every second day over a period of 53 days. And a certain parameter plotted over time then looks like this. Here you can see the temporal development of the seawater alkalinity, where each line here is representing one mesocosm. For example, then the temporal development of the mesocosm with an alkalinity increase of 300 and simulating the silicate-based mineral is depicted as this green line here. And you can see that in our experiment, the alkalinity level in the seawater was fairly stable in all mesocosms. To then analyze if alkalinity or the mineral type is affecting a biological parameter, I conducted linear regressions, as you can see down here in this figure. Here you see the phytoplankton biomass changes relative to the alkalinity level. So each data point in this plot represents one mesocosm and is the average value over the time of the experiment. So the before mentioned mesocosm would, for example, be represented as this point, and with an increase of alkalinity of about 300, and the simulation of the silicate-based mineral illustrated by the green color. And here you can see a large variability in the data points, meaning that there is no significant effect of the increased alkalinity or the mineral type on the phytoplankton biomass. So if the phytoplankton biomass does not show any clear effect, the next question is if there are differences in the composition of the phytoplankton community. So as mentioned before, OAE and the applied minerals are assumed to cause changes in the phytoplankton community. However, when looking at the biomass of the calcifiers and the silicifiers, we did not observe any significant changes in their biomass. But when we're looking at the whole planktonic matter in the water column, we actually observe an effect on the elemental composition. So the carbon to nitrogen ratio is here a very fundamental property with various possible drivers and also many different consequences if it changes. And what we observe is that it increases with increasing alkalinity, meaning that with increasing alkalinity, more carbon relative to nitrogen is incorporated into the organic matter. But this is only significant in the scenarios simulating the silicate-based mineral dissolution. So to conclude, what are the ecosystem consequences of OAE? this experiment shows that there is an effect of OAE on the marine environment. And this effect is not only caused by the increased alkalinity, but it is also shaped by the simulated mineral types. And this is a very good starting point to further investigate on the drivers behind this effect and also what possible consequences it may have. So thank you very much, and I will hand over to the next speaker.
Hello. Hi, everyone. Yeah, so as David said, I'm Nathan Walworth. I'm an adjunct assistant professor at USC and the VP of Science Strategy at Vesta. So at Vesta, we implement a method called coastal enhanced weathering. This is where we take what we call carbon removing sand, which is just made of the mineral olivine, so a silicate mineral, and we take it to coastlines and we place that in coastlines, and as olivine dissolves, it enhances the alkalinity, it enhances the capacity for the ocean to take up CO2. So I'm just going to go through a few of our studies, or sorry, a few of our results in a study that we did this past year. So as you know, in addition to potential co-benefits of ocean alkalinity enhancement that include ocean acidification, our company specifically also interfaces with another industry, the coastal protection industry. And this is an industry that takes just normal upland sand or dredge sand to coastlines to shore up erosion. And as we know, erosion is being experienced around the world by different places and different coastlines. So on the right, you're just seeing a graph about in this industry where the volume of sand is increasing over time, and to date now we have around 37 million cubic yards of sand placed in U.S. coastlines each year, independent of us, of course, and that's in the U.S. alone. So just a little bit about our team. We're principally a remote organization, and we have people in different research stations that we occupy, and so we do have to collaborate a lot with different institutions at those local sites or those local research stations. So this is just a few of our collaborators. So before I go into the field pilot, I just wanted to show a quick graph of a field study that we actually did in Papakolea, and Papakolea is a natural olivine beach in Hawaii, and that's what you see in the colors here. Green is the Papakolea beach, which is like 40% enriched olivine, and then we compared it to nearby beaches that experience similar oceanographic conditions except for a reduction or minimal to no olivine concentration. So what we were interested in we're seeing, what does an olivine beach look like, especially after millennia of weathering, and are there differences in, for example, trace metal content in the infauna across the beaches. So we collected worms, amphipods, bivalves, corals, fish, and in collaboration with the University of Antwerp, we analyzed their trace metal content, and we saw no statistically significant difference across these beaches. So this was sort of like a nice idea of an end member of, if you were to place olivine in an environment and sort of what the fauna may experience there. So over to the field pilot. So in July 2022, we executed a small field pilot in New York, and we did this in collaboration with Cornell Cooperative Extension and Stony Brook University and the town of Southampton. And so how this unfolded is the town of Southampton, like many towns, are experiencing a lot of erosion, so they regularly do beach nourishments. And so the town of Southampton already had a permit to do beach nourishment, to place 10,000 cubic yards of sand down in order to shore up a part of the beach called the North Sea Beach Colony. And so when Vesta was talking with the town of Southampton and the coastal engineering firm, we chatted about potentially adding 500 cubic yards of olivine on top of their existing beach nourishment project, so around 5% of the total sand volume of the beach nourishment. So we submitted a permit amendment to just add this sand, and it was accepted by New York State, and we were able to place 500 cubic yards of sand after the beach nourishment project. So to us, this represents an interesting path where, for field pilots, where there was already going to be an activity of placing sand that Vesta could then measure some of the olivine sand on top of that. So on the left, you'll see a bit of the design of the experiment. And it's a little tough to see, but on the very left is one control area that had no nourished sand. And then the purple box with the diagonal lines, that's really where we placed the olivine, as you can see in that picture. And then the larger orange box was where the other nourishment happened. So the larger 10,000 cubic yard nourishment of just dredged sand. And so that kind of served as a control site, that nourish site without the olivine. And then we had another control that was just adjacent to that. So these are just a few pictures of our engagement with the community and some of the high school interns with collaboration, and we are continuing to do this engagement today. So this is just a bit of a snapshot of our monitoring program. It's a before-after control, impact design, Baki design, and we do a minimum of 2 years of monitoring. Happy to go into depth with any of these methods after the talk, but just wanted to show a suite of what really kind of just looks like a coastal oceanography project in the monitoring program. So just a little bit about some of the preliminary data that we're getting back that we're still analyzing. So we deployed an XO2 sonde to just measure basic water quality metrics. And we also had the benefit of looking at the data from other nearby sondes or water quality stations from the USGS. And that's what you're seeing here in this plot, where in the green line is our sonde, and then the blue and the red is USGS. And so top line is chlorophyll A, middle is pH, and lower plot is dissolved oxygen. The yellow bar going down the middle is the olivine deployment. And after extensive monitoring, we saw no discernible impacts on key water quality metrics across all of the sondes, which was a good sign for us, and showing that sort of the wave action after we placed the olivine generally diluted out in many of the metrics in the water column. So we also did benthic community surveys. So as you can see here on the left is abundance, and on the right is species richness. And we have the 4 treatments that I mentioned, olivine being the green, and then we monitored across these seasons. And so for both abundance and richness, we observed no differences between the treatments and the post-deployment controls in these months following the deployment. We conducted an additional study that was not necessarily required, but we moved forward with Stony Brook and Cornell, where we actually placed oysters in bags across the different control sites and the olivine site. And as many of you know, oysters are an indicator organism for trace metal concentrations and bioaccumulation in the water column. And after 2 months of these oysters sitting in olivine sand, we did not also observe any differences in trace metal content relative to the controls. And here's just our plots of some of the initial data around carbon removal, which we feel is really exciting, and there's still more work to do and more to measure. But here, what we did is we deployed benthic flux chambers. As I'm sure everyone's thinking, it's placing olivine in natural environment and understanding how it spreads over time. That's part of our approach. And one of the things that we employ in order to understand if olivine dissolving within the pore waters is fluxing olivine dissolution products to show carbon removal are these benthic flux chambers. So these benthic flux chambers, they trap a parcel of water, overlying water over the sediment, and we put them in the control sites and the olivine sites. And what I'm showing here is a graph of pH on the top, dissolved inorganic carbon in the middle, and total alkalinity on the bottom. And what you want to see in terms of a carbon removal proxies is you want to see alkalinity and pH increasing, but dissolved inorganic carbon staying the same because there's no change in DIC as you transfer PCO2 to DIC in the water. And so that's exactly what we see. And this increase in pH also is an indicator of the counteracting effects of ocean acidification as well. So we were really encouraged by these results, and we're developing more advanced methods to monitor this over time, along with models, of course. But this was a great empirical sort of first step for us to see proxies of this carbon removal. So with that, I'd love to thank you for your attention.
Great, thanks for the invitation. Excited to share some initial results from testing ocean alkalinity enhancement in seawater. So these are experiments from the CMATE program at Stony Brook University, and then also from Ebb Carbon. So just to put what we're doing in context of all the other OAE pathways, what Ebb does and what the CMATE project is testing as well is taking saltwater or brine, waste brine stream, and aqueous brine stream using electrochemistry to process that alkalinity source into aqueous sodium hydroxide. So that is the form of alkalinity that we deliver, and that is dispersed, mixed with the desalted brine and put in the surface ocean at coastal locations, and then just kind of putting it in the larger picture of other companies like Vesta and so on. You can kind of categorize this by what source of alkalinity, how you process that to get to the ultimate alkalinity type, and then where you disperse it. So this is just where Ebb sits in that universe. So our roadmap goals first is to demonstrate the efficacy of CO2 removal. So there's a check mark there. I'll show you some data from the CMATE project showing that. And then demonstrate safe bounds of alkalinity enhancement, and that's ongoing, and I'll describe some of those results. So first, the CMATE project at Stony Brook, designed to really test the chemistry of the process, right, and the effectiveness and the safety of the chemistry of the process. At Ebb Carbon headquarters in San Carlos, California, we're building our commercial scale system and testing that. So it's system performance and safety. And now we're at the readiness testing stage where we're taking that commercial scale system from Ebb, putting it into a site where we could potentially pilot if the readiness testing shows that it's effective and safe to do so. So that's where we are now. And in fact, I just got a picture this morning that the system was disassembled on a truck headed to the readiness testing site. Okay, first some results from the CMATE project at Stony Brook. So this is at Flax Pond Marine Lab on the north shore of Long Island. And so we're pumping water from Long Island Sound for these tests. So our objectives here are first to verify the chemistry of the process. Does carbon dioxide from the air, are we removing CO2 from the air and storing it in bicarbonate and dissolved inorganic carbon? Number two, what are the kinetics? How long does that take? How long does it take for equilibration to happen? And then three, important for pilot and field studies, is establishing safe thresholds to avoid magnesium hydroxide and calcium carbonate precipitation. So we want to avoid calcium carbonate precipitation because that partially undoes what we're doing. That precipitation process releases CO2 into the water, and we want to avoid magnesium hydroxide precipitation because that increases the turbidity in that mixing zone, which is not ideal for safety to marine life. Okay, here's a picture of the tests at Flax Pond. So this is Long Island Sound seawater pumped into approximately 6,000 liter tanks. One of these tanks is designated as control, so nothing happens to that tank, and the other tank is the experiment tank. We dose aqueous alkalinity, aqueous sodium hydroxide into that experiment tank until the bulk pH is some set target value. So there's some very gentle circulation. You can see the surface of the water is still, but there's enough pumping that the turnover rate's about once per day for each of these tanks. So here's just an example of data from one experiment where we took the bulk pH of the experiment tank to 8.5. I won't go through every single line here, but what you want to see, so the experiment tank is solid and the control tank are the dotted lines. Blue is on the left-hand axis and red is on the right-hand axis. And what you want to see is, first of all, you can see total alkalinity for the experiment tank is higher than for the control tank because we've added the alkalinity, and it's constant throughout the experiment. So that's good because it's saying that we're not precipitating out calcium carbonate or magnesium hydroxide, which would remove that alkalinity from solution. The second point, if you look at the pH plot, the second one down, the experiment tank starts at pH 8.5, and then over time, that pH is decreasing, presumably because CO2 is coming into the water and being stored as dissolved inorganic carbon. To verify that, we measure dissolved inorganic carbon, which you can see third from the top, and you see the DIC is increasing over time in the experiment tank. So all of this pointing to the fact that indeed carbon dioxide chemistry works. Carbon dioxide is being pulled into the water as DIC. And the time scale is for these tanks, and this depends on the scale of the tank and the mixing in the tanks, but for this experiment it's about 30 to 40 days, which is in line with what it should be. Another important thing to check is how much dissolved inorganic carbon increase do we get for an amount of alkalinity we add. So the carbonate chemistry, the carbonate system equilibrium constants tell us that this should asymptotically approach a value of about 0.8. So in other words, 0.8 moles of carbon dioxide removed from the air and stored as dissolved carbonate, dissolved inorganic carbon, per mole of total alkalinity we add. And so for 3 different experiments where we take the tank to different pH levels or have different airflow levels, you can see that they're all asymptotically approaching 0.8. The blue experiment, pH 8.7, we just stopped before it reached equilibrium. Okay, so those are the CMATE experiments at Stony Brook. Moving on to Ebb Carbon, our headquarters is in San Carlos. If you're ever in the Bay Area, send me an email and happy to give you a tour. It's a fun place to visit. That system is our first commercial scale system. So operating at full capacity, that can remove 50 tons of CO2 per year. You can see it's in the form factor of a shipping container for good reason. And in fact, this could be expanded to 100 tons per year by just adding another one of these, the beige half-meter squares you see at the bottom right, which is the electrochemical cell. In the back left, what you see there are the tanks. So you see 6 IBC tanks, salt, acid, base, input, output. And this system is that I just saw the picture of this disassembled on the truck headed for readiness testing. Before we did that, we fully tested it at our headquarters, and just one result there that's important is for performance is energy consumption. So we're right where we want to be, between about 1 and 2 megawatt hours per ton of CO2 for the electrochemical piece, which is the bulk of the energy demand. And you can see a slight decrease in the energy required per ton of CO2 as the brine concentration increases. And the reason for this is essentially higher brine concentrations mean that some of the work that we're doing by applying electricity is done naturally by the chemical potential in the brine. So for us, higher concentration brines are even better. What's next is this readiness testing stage. And the goal here is to just really carefully lay scientific groundwork for the efficacy and safety before we go to the piloting stage. So once that's at the site, testing the system at the site under real world conditions, understanding the effects of OAE on marine species and ecosystems, that will be part of that readiness testing with our partners. Developing new oceanographic tools, including modeling with our partners for OAE at this specific site. And then we're in the process of developing our MRV protocol and really developing that specifically for this site to be ready to pilot. So lots of thank yous. First of all, to the Stony Brook team, funding from the Grantham Foundation for the CMATE project. They funded a lot of early work in Ocean CDR and I think helped get the field started. So really a big thank you to them for this project and others, I think. At Stony Brook, those tank tests were really led by Mallory Ringham, a postdoc in the group who will be EB's head of MRV starting in May, and also Shi Lu, Nathan Hurdle, Cody Shaw, and Catherine Hillis, who's an undergrad, did great work. Collaborators on the CMATE project, Brendan Carter at University of Washington and NOAA is PI on the CMATE project, so he and Julian Herndon at NOAA and UW. Everyone at Ebb Carbon, and then thank you to Ocean Visions, who provided scientific advisors for the CMATE project. In addition to we're part of, Ebb Carbon is part of the Launchpad program for the X Prize carbon removal, and so providing as scientific advisors for that as well. So thanks for your attention. Looking forward to the discussion.
Can we pull Anna up on the big screen here?
Gerne, bitte.
Great, there we go, thanks. So those were really great talks and lots of food for thought here. I have a few questions I want to ask some of the panelists to get us started. And then I want to make this as interactive as possible, so I want to give lots of time for the audience to ask questions, because I'm sure that all of you have really great questions for our panelists today. Let me start with you, Anna. You know, you were talking about mesocosms, and mesocosms are really great. They're helping you understand ecological dynamics and environmental impacts, but they're not open, uncontrolled systems. And so how much can we extrapolate the findings that you're learning from these mesocosms when we think about what a large-scale testing might actually look like in an unconfined system without walls like your mesocosms?
Yeah, so the approach of the mesocosms is currently the one which is closest to field testing. And it certainly gives a very, very good first idea of what to expect of real-world application of ocean alkalinity enhancement. So what we can really draw from these results is the fact that we will have an effect on the marine ecosystem of ocean alkalinity enhancement. But the problem is mainly that we are still at the very beginning of the research in general. So even this is not yet field testing, and even this mesocosm, kind of this experiment of this large scale, is only the second one worldwide. So the results that are presently available are very limited with respect to location and season. So this is, from my point of view, even more, because of this, it's even more difficult to already draw conclusions for what we can expect of a real-world application.
Thanks, Anna. I think, you know, what you mentioned is a really good point, that even though we're making a lot of forward progress on field testing, that this, what you said, this is only the second mesocosm experiment in the world, also points to the long road that we collectively have ahead of us, and really the need for accelerated R&D. I want to turn my attention and ask Matt. You talked about some of the work that you're doing in the lab. You talked about the plans to move to the field. And what do you see as the biggest roadblocks along that journey?
Yeah, I guess I'll just repeat something I said yesterday, because it is maybe the biggest roadblock, especially in starting to get into the water and pilot and scale, is just having a clear permitting structure. I mean, I think it's understandable. This is a new thing, so it's not complaining. Obviously, there's an existing permitting structure that we're going through now, and that's understandable. But as we think about moving forward, I think it would be extremely helpful just to have a specific permitting structure and clear rules and regulations, what data is needed to go forward, so that everyone's just clear about that.
That does seem to be a consistent theme emerging from the Ocean Vision Summit. Let me turn it over to Nate. You know, Nate, in your presentation, you were showing such a wide range of collaborators that spanned industry and government and universities, and I'm just wondering if you can touch upon both the opportunities that that's presented and the challenges of working across those different sectors.
Yeah, definitely. It was definitely a journey to figure out that space, and our legal counsel, bless his heart, you know, helped us with all of those collaborations. So I think the opportunity is, you know, for us at Vesta doing coastal enhanced weathering, you know, we're naturally, you know, our technology is naturally out in the environment. And so a lot of our program, if not most of our program, a lot of the times is first doing ecological impact and environmental, you know, type studies. And all of that is best done by universities, local universities with that infrastructure there that know the local environment. And in that way, we could, that's how we partner a lot with those universities, is to first ensure that whatever we're doing has a safe framework before, you know, the idea of carbon removal. So with them there we could do things like publish, and things can be open source and in the public benefit. And, you know, Vesta is a public benefit corporation, and then we have a hybrid 501c3 nonprofit structure, so that we can take in the right type of capital to do specific experiments with. So for environmental safety experiments, we could use potentially like donations and things like that. So that's a great opportunity. For doing carbon, like developing MRV, that's more of a challenge to collaborate with. I think as many of you know, at least in the United States, any work done on a university campus, of course, there's intellectual property considerations that you have to work through if there's commercialization potential. And so for us as a startup, it's already hard. Our intellectual property is already hard in this space because of the need for transparency for MRV. So when we have to create defensibility for investors, we have to really carve out like why we are defensible. So we have had to create specific approaches so that we could do this work at remote labs that we set up, which was all really difficult. And we have a path for that, but that was some of the challenges. And then generally timing challenges, I think we're all well aware of is, universities have one type of timeline and us with our runway have another type of timeline. So we just had to kind of figure that out in real time. But I think, everyone that we worked with is very understanding and people wanted to see this move forward. So that was, very promising. And then, that's a little bit of the challenges that we have so far and will continue to have for some time.
Matt, anything you want to add?
No, I think Nate covered it. Yeah.
Great. Well, this is really great. We have plenty of time to get the audience involved with Q&A. So just like with the other sessions, there's some microphones up here. Please come and ask away. Ask the tough questions to the panelists.
Yeah, hi, good afternoon. Cohen Bauer, Ocean Networks Canada. First of all, thank you very much to everyone for their great presentations. My question is specifically to Matt. I'm wondering if you could comment on the most promising uses for the acid byproduct that's generated in your process. And specifically, in the context of the real-world field trial, are you seeking to figure out what that pathway is in the context of those field trials, or is this issue being dealt with sort of separately? So,
yeah, thanks for the question, Cohen. So we are dealing with that for each pilot, right? So it's not like we're separating it. And we also are making sure that the solutions we come up with for the acid use are scalable to gigatons. So along those lines, the most promising gigaton scale use for the acid that we produce along with the base is enhancing CO2 mineralization, and that can be ex situ or in situ. So there are teams looking at ex situ mineralization in rocks and also in situ. And I think in situ is interesting because, for example, in Iceland, that's happening now, right? And so in those cases where those injection rates start to increase, and if those rates start to decrease, pre-treating with acid to increase surface area, release some of the cations, can increase the rate of that reaction. And so you can imagine in the future some kind of alternating acid pretreatment with CO2 injection to increase kinetics and then also increase the capacity of CO2 mineralization. So that in situ is longer term, but I think that could be quite large scale because in the future a lot of companies will have CO2 gas that they want to mineralize and inject. Ex situ is kind of more tractable near term, and so for our pipeline of sites, we are putting in place partnerships with companies pursuing ex situ mineralization to have that on site. And then there's sort of a more distributed, smaller scale option for even more near term, which in our first pilot site we will use, which is sand and gravel companies are sort of everywhere just by the nature of the industry, and they have alkaline waste that is a pain point for them. They need to deal with it in some way. And so neutralizing those is kind of a near-term path. Yeah.
Much.
Hi, I'm Pete from Planetary. This question is for Anna. I am not an ocean biologist. You mentioned that there was a correlation between the carbon-nitrogen ratio. Can you explain a little bit more about that and talk for just a second about what the implications of that might be? Thank you.
Yeah, So the carbon to nitrogen ratio is kind of a ratio of how much units of carbon and how many units of nitrogen are in the organic material that we collect in the water column. So yeah, if it increases, we have more carbon. If it decreases, we have less carbon and more nitrogen. So this can have multiple implications. For example, it changes the food quality and the grazing pattern. It can also, it can also determine the fate of the organic matter, kind of how much it gets remineralized, and it also determines a little bit. It also determines the magnitude and efficiency of the biological carbon sequestration.
Great. Let's turn to some online questions.
Great. So there is a series of online questions that are about establishing mesoscale experimentation permission. So people wondering a little bit about what the process is like in Europe and in North America, and what might be easier than the other, and how that might be different from other areas.
Let's start with maybe Matt on this one, since you've had some mesocosms going.
Yeah, so the mesocosm work we'll be doing is with partners at that pilot site. So in that case, they were permitted to do those already, and those in the near term actually will not be in the water like Anna described. That, I mean, they'll be indoors to start. So that was pretty straightforward so far.
And can you talk a little bit about the flax pond setup? Was that?
Yeah, so the flax pond setup is different because those are in tanks. I'm interested in Anna's answer to this question because they were really in the water. So in the flax pond case, that marine lab is existing and permitted already, and we're doing indoor tank experiments. So I think it's more straightforward in that case.
Okay, Anna, tell us the challenges of real in-water testing.
To be honest, I don't know that much about the governance on of the restrictions, the challenges that you face when you want to conduct mesocosm experiments. Sorry, I can't say that much to it.
That's okay. I think just for some historical context, your advisor, Ulf Riebesell, had some of these things in motion for a long time before you started, and so people could reach out to him if they have some questions.
Yeah.
Looks like we have another live question here.
Hi, Colin Sonicson, Dartmouth Ocean Technologies. Nathan, this is a question for you. I'm just wondering, in the first few of your slides there, you showed that the U.S. is putting 37 million cubic yards of sand on their beaches. I'm just wondering, if you have 5% of that as olivine, what kind of, does that translate into the gigaton scale of CO2 removal we need to do?
That doesn't translate necessarily into the gigaton scale, and the amount of carbon removal that happens is dependent on different oceanographic conditions. And that it's difficult to say now because for us at Vesta, what we're focused on, I think, like with Matt and a lot of other companies, is just ensuring that things can be safe in the environment, even at just like a very small scale. And so we haven't necessarily really gone forward with that type of scale and thinking of creating those projects. But what I can say is, that the coastal nourishment industry is already taking off independent of us. It provides a bit of a precedent in that there is a permitting precedent for placing sand. Obviously, our sand is different than some of the sand that is placed, but we go through all of the normal sort of like EPA testing for before we place anything in the water, just like any other coastal nourishment can do. So yeah, there is it's a positive kind of sign for us in that there is precedent around the world in using sand to place in shorelines, and so that provides a framework. But again, since this is so new, obviously there are a lot of conversations happening right now if an independent path can be achieved. But I think for us at Vesta, we've been, as a human society, been placing sand at scale in many places for a long time. So there is a path to scale if things are proven safe across those increasing scales. So yeah, just to your question.
Corey Myers, Lawrence Livermore National Laboratory. This question comes from a place of ignorance. If we're going to deploy a project at maybe several hundred thousand tons, maybe a megaton in a local environment, how long do we need to, look at the effects on the local environment to ensure that it's safe? And is that something that we're going to have to do on every project as we scale up? Thank you.
Great. That is one of the questions, I would say. Yeah. So the way that we're generally thinking about it again is, what we do at a very small scale, if and when we do a field pilot, is the minimum 2-year monitoring. Thinking about, what it means to be at that type of scale, which inevitably, we think it probably won't necessarily be, adjacent, up on the beach for us. It'll be in other areas in deeper water, most likely. Still, on the shelf, but deeper water. I'd say right now that is part of, what we want to work with the scientific community to determine. I don't think there's a specific answer. We know that, intensive monitoring has to happen post-deployment for some time. And then I think those initial data sets will give us insights into exactly how, ecosystems are responding to a project of that scale. What I didn't mention is, such a big part of Vesta's development and approach is actually the design of a placement, for example. So that's very much a coastal engineering type of activity where a lot of other things are taken into account aside from just sort of the geochemistry. And so that's what we're actively working on right now, is really what are the scenarios and the simulations to design potential deployments of that scale that can maximize safety, but also carbon removal. And, is it really thin layer across a very long swath of ocean rather than, something concentrated? The time to monitoring, I think this will have to parallel advancements and other things that are happening here at Ocean Visions, whether it be autonomous sensors and into modeling. But I think we'd have to treat it as a progressive project of monitoring and seeing what the data begin to show us over time. And that's why we obviously need to step up in very small sort of increments until we believe it's safe. But here's your thoughts.
Yeah, I'll give a somewhat short and maybe unsatisfying answer. We have a little bit different case than Vesta because our alkalinity comes out of existing outfall, so there's a mixing zone where the maximum change occurs. So in our case, I don't think from the question of safety, I think what we need to do are lay the foundation of the studies, establishing what are the safe thresholds. And because we know the maximum change is happening in that mixing zone, and because we have sensors in that mixing zone that feed back to our system and allow us to ramp the system current, up and down, in other words, ramp the rate of alkalinity delivery up and down to make sure we don't exceed them. I think if we lay the foundation of what the safe thresholds are, then because we're monitoring that maximum change region, we can make sure we're within those bounds. And that raises kind of a request for me, which is, the more people trained in the field to do these studies of impact on marine organisms in this direction of alkalinity enhancement. Lots of work has been done in ocean acidification, but I think we need more researchers and more of the scientific community to start laying that scientific groundwork. And please, anyone who's interested in doing that, reach out, and we're happy to describe here are the changes typical of our system, so that then we could simulate those in the experiments and understand what those safe bounds are, if that makes sense.
Ken Missler-Whittle. I appreciate the data, and I don't want to focus too much only on the beach sites, but these are erosional sites. So do you ever try and do a mass balance? Because those sites, by their nature, a lot of that material is going to be moved somewhere else, maybe deeper. A lot of that material might be bioturbated, and some small fraction will dissolve, right? And that's the effect you want. So how well can you quantify those three pathways, say, in an open setting like this?
Yeah, that's another great question, and something we think about a lot. So, part of the approach, of course, when you place olivine, it's a bit of a double edge in the sense that, like, you do want it to spread, and then you do want wave action to, for example, accelerate dissolution. Also, as it spreads, it dilutes out. So you can dilute out probably like any types of impacts, and then so that's a good thing. And then at the same time, we have to go measure that and spread. So we're developing other methods to track the spread over time, both empirically and through modeling. And if you can kind of imagine things spreading in that way, what we would have to do per your sort of three examples, which represent three different scenarios, basically over time track what we think those alkalinity fluxes are, depending on sort of where we see different concentrations of olivine, and ending up and then essentially refining our models to understand and predict that spread. And then from there, there we can do things like benthic flux chambers, where we can begin to estimate that area and that flux, and then mass balance and sort of integrate it over time. Of course, there will always be a range that we will have to report and some confidence interval. And for Vesta, the dissolution of olivine or the olivine grains, there's half-lives associated with it, and then some longer tails of dissolution. That's really where we'll probably meet the market and work with people to understand how to price in some of that uncertainty. So like, if we believe we can have a solid confidence interval for a certain amount and at scale over time, but then there's a longer dissolution tail that's in, now we're getting into like the 60, 70 years, there'll probably be a split in sort of that model. And to your question, Ken, that's kind of one of the main tracks of our research program.
Hey, I'm Dan from Carbon Blue. Thank you for the fascinating panel. My question is directed to Matt. You've shown that the energy consumption of the process decreases as the salinity increases using brine. I just wondered if you included the energy to produce this brine, because this is by itself requires lots of energy.
Great question. No, so that is just measuring energy consumption for generating alkalinity from a brine of that concentration. So your question is essentially, where is the energy to make that brine more concentrated? So there may be cases, an example would be a desalination plant, right? Where the waste brine, their waste is already more concentrated than, for example, seawater. And so I think it just means that those are even more helpful for us, because we would have to spend less energy converting it to alkalinity. It's not the case. I think it would never be worth it energetically for us to concentrate it to get that benefit in energy reduction.
Thank you.
Yeah.
We have time for about one more question. Does anybody want to get up and ask a question if they haven't already?
Hey, thank you everyone for your hard work. I know how much work experimental data is to collect, so thank you. This question's for Nathan. The benthic flux data you showed was really impressive treatment effects, but I imagine that was fairly soon after spreading the olivine. So I think not just for Vesta's approach, but for any kind of distributed environmental enhanced weathering, kinetics over time is a big question. So do you have a sense of how those rates change over weeks, months, years?
Yeah, great question. So, paired with these in-field testing is other kind of mesocosm experiments we are doing to help constrain dissolution rates over longer time periods. For example, we are doing mesocosm studies that will be much longer. with the goal of trying to recreate different conditions that we might experience in the coastal zone, as you know, in those benthic flux chambers and trapping a parcel of water and removing advection, it becomes difficult to constrain that exact rate in that way. We have certain approaches where we can estimate sort of how the kinetics can change over time, depending on sort of like the saturation state of the pore waters and things like that. So we have sort of initial half-lives that we're pretty confident in, and then sort of the tail that I was talking about. That's a big part of not only the empirical research, but constraining the models that we're using so that we can present that range. So at certain micron grain sizes, we have a pretty decent handle on the half-lives in the beginning, and then the tails are really something that we are constraining now.
Great. Well, let's wrap it up there. Please join me in thanking the panelists. And coming up is the keynote talk for the human adaptation to a changing ocean track.